And Everett says that's because you need to think harder about what you mean by looking at something. And when you're doing that, you have to take quantum mechanics seriously. Taking quantum mechanics seriously to Everett means two things. Number one, you can't pretend that you're classical. You can't pretend that even though you're a big macroscopic observer, somehow you're free from obeying the rules of quantum mechanics. You're just as quantum as anything else. You're made of atoms. So you should obey the Schrodinger equation also. You should have a wave function. If electrons can be in superpositions of possibilities, you can be in superpositions of possibilities. That's one fact. The other fact is this idea that Einstein and others developed in the 1930s called entanglement. This is really what makes quantum mechanics special and interesting, is this phenomenon of entanglement. So I'm going to introduce it by a modern example, but there were examples way back in the day. We recently, in 2012, discovered the Higgs boson particle, right? A new fundamental particle of nature, the last piece that we needed of the standard model of particle physics we discovered at the Large Hadron Collider in Geneva. And a Higgs boson is special because of all the known elementary particles, it has zero spin. Elementary particles can spin just like the Earth spins around its axis, but at the particle level, individual particles have specified amounts of spin that are very definite numbers. So something like an electron or a quark can either spin clockwise or counterclockwise. As physicists say, spin up or spin down. But a Higgs boson has exactly zero spin. And the important thing about spin is it's conserved. It's not created or destroyed. The total amount is preserved. So when a Higgs boson decays into two particles, like let's say an electron and a positron, an anti-electron, or a quark and an anti-quark, a spinless particle is decaying into two spinning particles. But the total spin has to be conserved. So what you know is that the two particles that it decays into better be spinning in opposite directions. You don't know whether this one is spin up and this one is down, or vice versa, but you know they're opposite, so the total spin adds to zero, because that's what it started from. So quantum mechanics says you don't know what the spin of the first particle is going to be. It could be spin up or spin down. But you know that there's a relationship between the spin of that one and the spin of the other one. So the wave function of the Higgs boson, once it decays, is into a superposition. A superposition of particle 1 is spin up, and particle 2 is spin down, particle 1 is spin down, and particle 2 is spin up. If you were to observe the spin of particle 1, you don't know what answer you're going to get. It could be spin up or spin down. If you observe the spin of particle 2, you don't know what answer you're going to get. It could be spin down or spin up. But if you observe the spin of one of them, and let's say you observe spin 1, particle 1 has spin up, then you know what particle 2 is going to be. It has to be the opposite to balance out. That is quantum entanglement. You don't know, there's no definite fact of the matter about the spin of either one of the particles, but there's a relationship between them. And this is a feature of the fact that there's a deep, deep feature of quantum mechanics which really makes it different than classical mechanics. In classical mechanics, if you have two particles, particle 1's doing something, particle 2 is doing something else. There's a state of particle 1, its position and its velocity and its spin. And there's a state of particle 2, its position and its velocity and its spin. You might think that in quantum mechanics, every particle has a wave function. And sometimes we even talk that way. So particle 1 could have a wave function that's a superposition of spin up and spin down, and likewise for particle 2. But no, that is not how quantum mechanics works. There is only one wave function for all the particles at once. There is only the wave function of the universe. And in this case, the wave function of the universe is this particular entangled superposition. Okay? This is probably, for the first two-thirds of the talk, this is the deepest concept I'm going to lay on you. So you got to understand this, entanglement. You don't know what particle 1 is doing or particle 2, but if you were to measure 1, then you know what you would get if you were to measure 2. So let's apply this idea of entanglement and the idea that you yourself are a quantum system to the Schrödinger's cat experiment. That's what Hugh Everett suggests that we do. And there's no special role played by observation or measurement or consciousness. You're just a physical system obeying the laws of nature, okay? So you have the cat It is in a superposition of awake and asleep, and you have the observer, now played in that role by Hugh Everett. And the idea of measurement is you open the box and you solve the Schrödinger equation. And the Schrödinger equation describes the cat, but it also describes you. So there's, again, absolutely no ambiguity about what the Schrödinger equation predicts. Before, in the Copenhagen interpretation, we made up a rule that says when you open the box and observe it, it collapses and you see one outcome or the other. Everett says, just do what the Schrödinger equation says. And the answer is that you and the cat evolved to an entangled superposition of the cat was awake and you saw it awake, plus the cat was asleep and you saw it asleep. Again, no one doubts that that is what the Schrödinger equation predicts. The puzzle is, it seems like you are now in a superposition of having seen the cat awake and having seen the cat asleep, right? But no one ever feels like they're in a superposition. No one ever opens a box and says, well, part of me thinks the cat's awake and part of me sees the cat's asleep. No, that's not what you think. So it's not crazy to think that Everett was crazy. It sounds like what he's saying is obviously wrong. And in fact, in some sense, he was ahead of his time, because the solution to this puzzle really wasn't well understood until the 70s or 80s, with the idea that we now call decoherence. Remember, I already told you that there's only one wave function for the entire universe all at once. But then I showed you a little picture on the last slide with the wave function of the cat and the observer. So what about the rest of the entire universe, right? I really should include the rest of the entire universe if I'm not cheating you. So we bundle up the entire rest of the universe. We don't keep track of everything. We call it the environment, represented here by some leaves of grass. But the environment could just be the photons or the air molecules bouncing around in the room. All of the things, all of the particles, all the degrees of freedom that we don't keep track of individually in our experiment. But you can tell if the environment is the air molecules or the photons in the box, they interact with the cat long before we open it, right? So that process is called decoherence, because the cat becomes entangled with the environment. If the cat's awake and over here, a certain photon might hit the cat and be absorbed, whereas if the cat were asleep, that photon just goes right on by. The way that the environment interacts with the cat depends on whether it's awake or asleep. So the cat very, very quickly becomes entangled with the environment. And that process is called decoherence. The observer just goes along for the ride until then they open the box, and then they become entangled with both the cat and the environment. Okay? This story I just told you is just a slightly more accurate version of the story I told you on the last slide. So why am I bothering to tell you this slightly more accurate story? Because you can show, using math and stuff like that, that this state of the environment, entangled with the cat, is perpendicular to this environment, entangled with the sleeping cat. And what that means is that what happens in the future in this part of the wave function is never affected in any way by what's going on in this part. They have become uncommunicative. You know, they do not talk to each other, they do not interact, they do not influence each other anymore. That's what decoherence really is about. And that's what measurement is, according to the Everettian version of quantum mechanics. Measurement is simply when a small quantum system becomes entangled with its environment. And what happens then is the wave function is a superposition, but the different parts of the superposition go their own way. What happens in one is independent of what happens to the other. They branch, as Everett put it. They split into two possibilities. It is as if those two parts of the wave function describe separate, independent worlds. And that is why the Everett interpretation has been dubbed the many worlds interpretation of quantum mechanics, because these two parts of the wave function, here and here, don't talk to each other anymore. We should treat them as if they have nothing to do with each other, as if they are independent. So what I want to emphasize is I didn't put in a bunch of worlds. All I did was take the Schrödinger equation seriously. The Schrödinger equation predicts the existence of many worlds. Every other version of quantum mechanics is a get rid of the other worlds interpretation, okay? And maybe that's worth doing, but Everett says, why bother? He says what happens when I just obey the Schrodinger equation is what was one copy of me is now two copies of me in the future, but they're separate people. They don't have any way to talk to each other or anything like that. Just take them at face value. There's two different worlds. That's it. Live with it. Chill out. Don't mess with the rules of quantum mechanics. People don't like this. It did not go over well. Everett's thesis advisor, John Wheeler, was another acolyte of Niels Bohr, the grand poobah of the Copenhagen interpretation, and many harsh letters were sent back and forth over the Atlantic Ocean. Let's just put it that way. Everett never even tried to get an academic job. He left to do defense consulting, and the interpretation was more or less forgotten. But it's been rediscovered. So there are good reasons to be skeptical, or at least puzzles yet to be answered within the Everett interpretation. But there's also a bunch of not so good reasons to not like it. So I don't mind if you come away from the lecture at the end of the day not believing the Everett interpretation, but I want you to not believe it for the right reasons, if that's possible. So let me try to ask and answer some of the simplest questions about this. The simplest question, to which I only have a very unsatisfactory answer, is how many worlds are there anyway? I just showed you a picture where, with the cat, one world branched into two. But with an electron, if you measure the location of the electron, how many different possible answers could you get? The answer is infinity answers, right? There's an infinite number of points in space where the electron could be located. So naively, and maybe even in reality, there are infinitely many worlds. The reality is we don't know how many worlds there are in the many worlds interpretation of quantum mechanics. There could be infinitely many, in which case you shouldn't talk about how many there are. You should talk about the relative weight of worlds acting one way versus worlds acting in another way. What I want to get across is, it's not, people worry sometimes about, conservation of energy. If I measure a spin and suddenly there's two universes, where did all the energy come from for the stars and galaxies in that universe? But what's really happening is, as time goes up, you start with one big universe. There's a lot of weight. There's a lot of wave function attached to this single branch of the universe. And through a series of physical interactions governed by the Schrodinger equation, that universe is divided up into multiple copies. It's not that you're creating new stuff. The universes are, in a very rigorously, mathematically well-defined sense, thinner than they used to be because they're differentiating from each other. You're not creating more stuff, you're just differentiating the stuff that was already there into many, many, many copies. The people who are in the copies don't know this, but that's what the math says. So don't worry about conservation of energy or anything like that. Another question is, I just don't like it because there's too many universes. I don't want to disparage this kind of question too much, but I'm just trying to accurately capture the fact that really the reason why people don't like the many worlds interpretation is because it seems too extravagant, right? You're trying to answer a simple question about electrons and you end up inventing an infinite number of universes. Doesn't that seem like bringing an awful lot of ammunition to bear on a fairly small little puzzle? But I think that's exactly backwards. I think that Everett really is the simplest, most straightforward reading of quantum mechanics. Remember, all the many worlds interpretation is the statement that there are wave functions and they obey the Schrodinger equation. The worlds are a consequence of that. You did not put them in. If you believe that an electron can be in a superposition of spinning clockwise and spinning counterclockwise, and you believe that the world obeys the rules of quantum mechanics, then you can be in a superposition of having seen the electron do one thing and having seen the electron do other thing, and the universe can be in a superposition. You can't stop liking it when the superpositions become big unless you want to change the rules of quantum mechanics in some way. And you are very welcome to do that, but that makes the theory more complicated. It does not make it simpler. Everett is definitely the simplest way to go. The other easily answered objection is that this can't be tested. You've made a lot of worlds, and you've already said that I cannot influence them in any way or be influenced by them in any way. That doesn't sound like science to me if I can't get there. But that's not right. Every theory makes predictions that can't be tested. We don't count it against a theory when it makes some predictions that can't be tested. We ask, what are the predictions that can be tested, and we test them, right? The typical criterion we like to use, it's not perfect, but it's pretty good, is falsifiability. Can we imagine an experiment that would tell us that this theory, if you got the right answer in the experiment, that would tell us that this theory is not correct, that it is falsified? And in the case of Everettian quantum mechanics, the only posits are wave functions and the Schrödinger equation. Could you imagine experiments that falsify those assumptions? Yes, they're being done. It's going on right now. All you have to do is observe an isolated quantum system violate the Schrödinger equation. There are theories in which that happens, and they are being experimentally tested right now. Everett is the most falsifiable theory ever invented. It just hasn't been falsified yet. All right. The other thing I want to say is that I mentioned before, it's not just philosophy. I don't want to denigrate philosophy. I'm a big fan of philosophy. I think that philosophy is important, and certainly empirically over the last several decades, philosophers of physics have done a much better job at taking quantum mechanics seriously than physicists have. But I do think that maybe we shouldn't be surprised that we're struggling with certain puzzles within physics if we have abandoned the quest to understand quantum mechanics for its own sake. If you claim, if someone like Richard Feynman can get up in front of the room and say, I don't think anyone understands quantum mechanics, and then someone else comes up and says, well, we don't understand the quantum theory of gravity, for example. Well, why should we understand quantum gravity if we don't understand quantum mechanics, right? This is not usually the way people think, because we tend to start with a classical theory and then quantize it. So the search for something like quantum gravity is starting with the right classical theory of gravity and then turning it into a quantum theory. But presumably nature doesn't do that. Nature doesn't start with a classical theory and then quantize it. Nature just is quantum from the start. Maybe the reason we don't understand quantum gravity is because we don't understand quantum mechanics. And I suggest this not only as a logical possibility, because I think it might actually be true. So just to remind you of how gravity works, for those of you who have not read my textbook on general relativity, our best current theory of gravity is Einstein's theory of general relativity. The motto for general relativity is, gravity is the curvature of space-time. So you have to believe that there's something called space-time, the three-dimensional space all around us, plus time evolving us forward. Einstein says you should think of space-time not merely as the background, as the stage on which physics happens. It's a player in the game in its own right. Space-time is dynamical. It warps, it bends, it changes in response to stuff in the universe, to matter, to momentum, to energy is the simplest way of thinking about it. When an apple falls from a tree, it's because the energy of the Earth has warped the space and time around it, so that falling is the simplest thing that the apple can do. So if you want the motto for general relativity, is that geometry of space-time is somehow related to energy. This is the thing that we would like to get out of a quantum mechanical description of nature. So as I already said, we don't understand quantum mechanics, we don't understand quantum gravity. Maybe these lacks of understanding are somehow related. And so the program is, rather than quantizing gravity, we should find gravity within quantum mechanics. We should start with a purely quantum idea, which, by the way, this is the point of doing Everettian quantum mechanics. In all other, remember I said there are alternatives to Everett. There are versions where there are hidden variables, there are versions where the Schrödinger equation is violated. In all of these, some lingering element of classical reality is put in by hand at the start. There are some classical presuppositions that come into how we get rid of all those other worlds. Everett is the most purely quantum of all the approaches to quantum mechanics there are. So if you want to play the game of starting with a purely quantum description of nature and seeing how the classical limit arises, playing it within the framework of Everettian quantum mechanics is the most natural thing to do. So that's